All right, we'll get started today. I think this is working. So remember that the homework deadlines were adjusted. So your second one is due, I believe, tomorrow night, and then a week after that for the third assignment. So there are gonna be two Tuesday deadlines, and then we'll be back on our regular Sunday schedule. All right, if you recall what we finished with last time, we went over one of the earlier models of how electrons behave in atoms called the Bohr model. Um, And before I get into that, I always forget about this. This is the first of our weekly installment on um, work habits and things in progress. So just a little bit about how the first assignments went. So the homework one and the quiz one. The average score for both was very high, 92% for the homework, 89% for the quiz. Um, Another thing that we can track is how long you spend on each assignment. I don't know if that means much for the homework because the homework is untimed, so you might just log in and then, forget about it for a while and come back. So I don't know if this number means anything, but the average person spent 109 minutes on the homework assignment. I'm guessing it wasn't actually that long. I'm guessing a lot of people entered the assignment and just forgot about it for a while and came back, which is no problem, of course, because it's not timed. Um, and if you're thinking about, and then for the quiz, we give you 120 minutes. It technically is time, but the average is only 24. So that number will probably get higher as the semester goes on because the problems will get a little bit more advanced and complicated, but it's not a huge amount of time that we're spending on it. And then the just if you're curious about which topics we had the most trouble with, that you might want to make sure that you're clear on them. For the homework assignment, the question with the lowest average score was number 10, which dealt with um, unit conversions, those that involve the prefixes, micro, nano, kilo, and so on, and putting numbers into scientific notation, which some of that might just be the syntax that you have to get used to on the homework. So make sure you're clear on that if there's any problems. And then on the quiz, the one that we had the most trouble with was the one that just dealt with mathematical operations, where we wanted you to report the number with the correct number of significant figures. So again, that's really only important for that review chapter. So it's not going to be a huge emphasis in the course, but it would be good to check in on that. All right, so getting into the material then for today, we ended last time with the Bohr model, which is the idea that electrons move in circular orbits around the nucleus, and then we had a series of equations that would predict the energy levels, and we could use those to then predict transition wavelengths, frequencies, things of that sort, like we did last time. Now, just like any model in science, chemistry being no exception to that, there's always going to be limitations or problems. And as we've already seen a few times in this course, when those limitations or problems come up, then it's the onus is on scientists to develop better models that address those and then test those out with a scientific method. So the problems that were pretty early on identified with the Bohr model is that it doesn't work at all if the atom has more than one electron. So the equations that we had, they work great for hydrogen or anything else that has one electron, which are some uncommonly encountered ions that would just have a single electron, but not very common. But if you have more than one electron, which the vast majority of substances on Earth do, then you have a problem. So the Bohr model does not work for the energy level. So those equations that we gave you that have just a single quantum number n and a function that allows you to predict energy levels doesn't work if the system has more than one electron. So it breaks down right away, even with just two electrons. So then the first attempts at rectifying the situation were to ask the question, well, maybe the orbits aren't perfectly circular. Maybe they're elliptical. Maybe they're oval shaped. Let's try that. So it's more mathematically complicated, but people try to do that. You can adapt the model to include elliptical orbits around the nucleus that aren't perfectly circular, but that also doesn't work. So long story short, that wasn't the answer. So again, Bohr model assumes circular orbits. If we make them elliptical instead, we can try that. And we can make equations and things and then use those equations to test the model, but that didn't work either. So no real improvement there. So the reality of the situation is that the Bohr model just does not quite get it right. empirically, the equations work for one electron system. So the equations that I gave you last time are not invalid. They can correctly predict the energy levels in hydrogen. They can use those to correctly predict absorption and emission wavelengths like we did. There's nothing wrong with the equations, but the physical model, the idea that electrons are circulating around the nucleus like planets are circulating around the sun, is just simply not correct. So the reality is that the Bohr model, as we said, only works for one electron systems. So those equations in particular, we're only going to use for hydrogen, and that's the only time they even work. And then the reality for hydrogen as well, but also for anything else, is that these circular orbits that the Bohr model put forth are just not correct. That's not really what happens. So when we're talking about how electrons behave around a nucleus in an atom, this idea that they move in circular orbits is just simply not correct. So again, even though the equations work for hydrogen, just the physical idea that the electrons are moving in circles around the nucleus isn't right. So that means, of course, you need a better, more advanced model to do this. And sort of cutting to the chase without giving a lot of the intermediate information, what was formulated to address all these issues is called the Schrödinger equation. So this is mathematically very complicated, so we're not going to give you the full story. It would require a probably at least calculus 3 level sort of mathematics to be able to fully understand it. And obviously, not even calculus 1 is a prerequisite for this course. So we're not going to go into the details about it. But we're going to tell you what it looks like. And of course, we're going to then tell you how we sort of use things in a more simplified and sort of a more physical picture, since the Schrödinger equation itself is pretty abstract at this level. So what the equation looks like, you're going to think that it looks like a pretty dumb and simple equation, but we have to sort of understand what these things mean first to draw that conclusion. So it's H psi equals E psi. Now you might be thinking like, well, that just means H equals E. Like I can do algebra, but that's not really all the whole story, because H here with a little caret on it is not just a number. It's what's called an operator. So you're basically, what you're doing is you're applying a set of mathematical operations to a mathematical function psi, which will also define, and then that returns the energy of the system. So it's again, it's mathematically complicated, so don't worry about all those details. But essentially, this H with a hat here, not cat, a hat, is called the Hamiltonian. So in this branch of mathematics and chemistry, the little caret on top of the hat means it's an operator. So it refers to a series of mathematical operations that you're applying to another function. That function being the Greek letter psi that we'll define here in a second. But it's carried out on this other function psi, the one that looks like a pitchfork, that will yield one of the allowed energy states for that system. So it's a series of mathematical operations that, when carried out on the wave function psi, the other part of this equation up here, will yield one of the allowed energy levels, which is what E refers to in this equation. Now, the important part for us to start to understand a little bit is this part of the equation psi, what's called the wave function. And the whole idea here, if you recall, last week we introduced this concept also of what's called wave-particle duality, which is essentially the idea that very small particles have both particle and wave-like behavior. And it turns out then to correctly describe how an electron behaves in an atom, or how a collection of electrons of its multi-electron, you need to describe the electrons as standing waves, not as particles orbiting a nucleus, but actually as waves. And that's what this psi is. So it's called a wave function because it is a mathematical equation that describes the electron as a wave. And we call it a standing wave because it's not a wave that's moving through space. It's one that's sort of around the nucleus, a wave that sort of a three-dimensional wave that kind of surrounds the nucleus as your origin. Describes an electron as a standing wave. And it can be parameterized in different ways, but we're going to sort of think about it in XYZ coordinates, which is the simpler way to think about it. So it's basically you have your nucleus as the origin, the 0, 0, 0 point, and then there's a three-dimensional equation that describes an electron as a standing wave in the XYZ dimensions. You can also do it, it's often done in polar coordinates as well, if you're familiar with polar coordinates, where you have your origin and you just have a radius and a set of angles that describes the position. It works for that as well. That's often how it'll be done in more advanced chemistry, but XYZ is the easier way to think about it, so that's what we'll kind of think about it as. And the key part about this wave function is, unlike the Bohr model, which says that electrons are moving in circles, and if we had an equation to describe that, you could predict exactly where the electron would be at any given time. A wave function doesn't tell you. It doesn't tell you exactly where the electron is. It tells you sort of it relates, as we'll see, to a probability of finding the electron in a certain place, but it can't tell you exactly where it is because the electron is behaving as a wave, not as a particle that's just moving around the nucleus. So we have to understand what this does and does not tell us. The wave function does not tell us where the electron's exact position is. And then when we're describing the different energy levels that exist in a multi-electron atom, so we saw in the hydrogen atom, in the Bohr model, you had these different orbits that were defined by values of n, the quantum number, and that reflect orbits that get further and further away. Similar situation occurs in the Schrödinger model and in multi-electron systems, where you have different energy levels. They're associated with different probabilities of the electron being closer or farther away from the nucleus. So they do relate to, on average, at least, how close the electron is. But each one has its own wave function. So each of those different energy levels in the atom is going to be described by its own wave function psi. And we'll give a synonym for wave function later on that's more often used in chemistry. It's called orbital. But basically, each of these wave equations describes one of the possible energy levels that an electron can occupy in an atom. Just like each of the circular orbits in the Bohr model describes one of the possible energy levels. Now, another thing that goes along with the Schrödinger equation is the Heisenberg uncertainty principle. And if any of you watched Breaking Bad, Heisenberg was not a manufacturer of illicit drugs. He was a famous scientist who came up with this idea, among other things, about and it sort of helps us understand why when we have a wave equation, a wave function that describes an electron or an atom, we can't precisely know where that electron is at any given time. And that comes out from what's called the Heisenberg uncertainty principle. So we're not going to do like much with the mathematics on this. We're going to more approach it from a conceptual standpoint. But basically the equation, it can be written in a few different ways, but one that we're going to use that's probably most relevant to what we're trying to convey here is this one here. And it's called an uncertainty principle because it sort of states the idea that this delta here is the uncertainty. It's how precisely can we know where the electron is? Is it exactly in this position, or is it somewhere in this range of values? That's what that delta tells you. Same here, the delta on the product of mass and velocity, the momentum of the electron. So the product of those two has to be greater than or equal to h, which is that same Planck's constant we've been using, divided by 4 pi. And so delta x, as we said, is the uncertainty in position. It's how certain can we be about where exactly an electron is at any given time, or any particle, really. M is the mass. And this is, again, one of those things where you might be thinking, how does this really play out in real life? How do we not know exactly where something is and exactly what its velocity is? I learned how to do that in physics. Well, again, it depends on the scale of the object you're talking about. So if I go back to the analogy I made earlier with de Broglie wavelength and me throwing a baseball to the back of the room to see if people are paying attention back there. If I do that, if you guys know relatively simple physics that you might learn here in Physics 1 as early as that, you could predict, if you know how fast I'm throwing the ball and the trajectory and everything, you could predict where that baseball is going to be at any given time. You might say, well, I know exactly where it's going to be. Why is there this uncertainty? Well, again, because the uncertainty based on this equation is related to h over 4 pi. H is a very tiny number. So compared to the size of a regular everyday object, the uncertainty in that is very, very tiny. So you can, with good precision, know that on the scale of that object. But if you're talking about an electron, which is excessively small compared to anything that we can easily comprehend, all of a sudden you're in a situation where this product of these uncertainties, where the electron is, how fast it's moving, that kind of product of those two uncertainties is relatively large compared to the size of an atom, the size of an electron that's moving around an atom, and so that becomes significant. So this kind of relates then back to the wave equation, where we want to understand that the key idea of this modern picture of the atom and how the electrons are arranged in the atom is that it's impossible to simultaneously know the position and momentum of a particle, and it particularly becomes important when you're talking about tiny things like electrons. And so that's why when we describe wave equations, wave functions for electrons, we can't say exactly where the electron is. We can only talk about it in terms of probability of where it is likely to be. And that's how we're going to introduce it today when we start talking about these wave functions in more detail. So it's impossible to simultaneously know the position and momentum of a particle, but as we said, this uncertainty relationship really only matters for very small objects. It's not gonna play out in your everyday life, but if you're talking about atoms, if you're talking about things that are excessively small like that, we do need to think about it. We do need to understand then that we can't precisely say everything we want to know about the electron at the same time. It's sort of limited by this uncertainty principle. So again, you don't have to worry about the math behind this. I don't think there's going to be any numerical questions that deal with Heisenberg uncertainty, but just understanding along the same lines as we talked about with wave functions that you cannot know exactly where an electron is in an atom. So let's just give a quick numerical example. Like I said, you're not going to actually do problems like this as far as I know. Don't quote me on that again because the homework assignments are all new and I haven't taken a look at all of them in detail, but this is just a demonstration, really, not a type of problem you'd actually have to do. So if we're measuring an electron that's moving really fast with a observed speed of 1.0 plus and minus 0.1 times 10 to the 6 meters per second, what is the uncertainty in this position? So this plus and minus 0.1 here, that's that uncertainty in velocity. We don't know if it's exactly 1.0. It could be 1.0, it could be 1.1, it could be 0.9, somewhere in that range. And that's what that plus and minus 0.1 tells us, is how precise do we know that velocity? It's within 0.1 of 1.0. So if that's the uncertainty in the velocity and the actual speed that it's moving at, what is the uncertainty in the position? And the mass of an electron is 9.11 times 10 to the minus 31st kilograms. Again, very, very tiny. So let's just do the math. Again, not that you'll actually have to do this yourself, but just to see how it works out. So we're using this Heisenberg relationship. Mass we'll assume is constant, so we can move it out in front of the delta, but it could be written as either delta mv or m delta v. In this case, the mass is constant, so we don't have to have an uncertainty in that. It is greater than or equal to h over 4 pi. So that means our uncertainty is at least as big as h over 4 pi when you take the product in this way. So what we're going to do is just put what we know. So delta v, as we said, is plus and minus 0.1 times 10 to the 6 meters per second. We really only care about the absolute value of that. So in more standard form, it's 1 times 10 to the 5th meters per second. So again, that's sort of the range of possible values for the velocity, somewhere in there. And then we're going to just solve for delta x, the uncertainty in position. How precisely can we know where that electron is if we've measured its speed to be 1 times 10 to the 6 meters per second with this uncertainty? So just rearranging the equation, delta x has to be greater than or equal to h over 4 pi times m delta v. And so we just plug the numbers in. H is Planck's constant. And again, this number is so small that it doesn't matter in most situations, but electrons are also small. So when we put the mass in down here, as we said, it's 9.11 times 10 to the minus 34. 31, sorry, we're doing kilograms. And then 1 times 10 to the 5th meters per second. So we just plug the numbers in and figure out what delta x is, the uncertainty in the position. 5.8 times 10 to the minus 10 meters, which in nanometers is 0.58 nanometers. Now you might think like, oh, well, that sounds tiny. Like, who cares if I don't know where the electron is within half a nanometer? That's a very small uncertainty. I'm okay with that. But keep in mind that this number here is 10 times larger than the hydrogen atom. So it underscores the idea that if we're trying to make a measurement of where exactly an electron is in a hydrogen atom, it's basically impossible to do because the range of values that we could come up with, if we know the exact speed that it's moving at, is much larger than the atom itself. So when you're at the atomic scale, the whole idea of this is that it's impossible to know exactly where the electron is. There's no equation that would allow you to do that because of uncertainty. Now, those are some of the more far out ideas that admittedly are conceptually difficult for a course like this. Let's talk about how we're actually going to think about these ideas in the context of this chemistry course and as well as the vast majority of chemistry that you would do in the future. So let's introduce some key definitions and understand then how do we think about these wave functions, which, as I said, they're mathematically complex. They're hard to visualize because we're talking about an electron behaving as a wave around a nucleus. We don't know where it is at any time. So how do we think about that? So that's what we're going to go into now, the way that we should start to really think about these things. So when we talk about an orbital, that's the term we're primarily going to use in this part. That really is just a synonym for a wave function. We'll have a slightly more precise definition coming up, but essentially we can think of it as just a wave function. And so it is a mathematical equation at its heart, but we're going to sort of break it down into simpler terms than that. But what it allows us to do is allows it to determine the probability of finding an electron in a given position. Now, what we're going to originally define this as are specific probability values for finding it at a certain location. The way we would really start to think about it in a little bit later on is more like where is the electron likely to be 90 or 95% of the time. We're going to sort of define a region of space where around the nucleus where the electron would be the vast majority of the time. Now, the reality is, as we'll see, these probabilities never go to zero. So if I have a hydrogen atom up here at the front of the room, there's a non-zero probability that its electron is at the back of the room. Now, it's a very, very, very tiny probability that it's that far away. The most likely scenario is that the electron is very close to the nucleus. And that's what we're going to how we're going to sort of define orbitals, the region in space where the electron is most likely to be at any given time. Okay, but to do that, we have to think of really two different ways of thinking about probability of an electron around a nucleus. So the first one is called probability density. It's the square of the wave function, psi squared. Okay, so this would be the probability of finding the electron at a given point in space. All right, so these wave functions psi are, as we said, they can be parameterized with x, y, and z coordinates. So if you plug in a specific value of x, y, and z, and then all right, we're given twice because I'm trying to talk right at the same time. But if you put in a specific value of x, y, and z, and then square the wave function for that value, so you just plug the numbers into the equation and square it, that will give you the probability of finding the electron exactly at that position. Now, as you said, that's not the most useful way to think about it because we don't usually care where exactly the electron has a probability of being, what one specific place. We care about more of the regions where it can be. So the more useful one for us is radial probability density. So that's given as 4 pi r squared times psi squared. So this would be the probability of finding an electron at a certain distance from the nucleus. So it's not saying that the electron is exactly at this position. It's saying what's the probability of finding it this far away from the nucleus? Nucleus at the center, some distance r from the nucleus. What's the probability of the electron being that distance away from the nucleus? That's given by radial probability density. And that's a more useful way to think about it, because what we really care about when we start relating this to how, to chemistry topics, why do these wave functions orbitals matter for chemistry? One of the things that we're interested in is how far away from the nucleus does the electron get? That can be important for us to think about. And also, to some extent, what is the shape of that region where the electron occupies? It's not always a perfect sphere, as we'll find out. So the shapes of these orbitals, these probability regions, is important as well. So this radial probability density is more useful in those contexts. So now let's talk about what it looks like for the ground state hydrogen atom. So in the ground state hydrogen atom, we're in the n equals 1 state. So let's look at what the probability density psi squared looks like and what the radial probability density 4 pi r squared psi squared looks like. So the psi squared function is pretty boring, and you're going to think that this looks a little strange, because all it does is just sort of decrease like this. It never, see, I need to do this right. It never quite goes to 0, but it's just sort of a monotonically decreasing sort of asymptotic function. I'm going to get it right this third time, I promise. It's going to get really close to 0, but not actually get there. I need to try to do that really carefully. There we go. Okay, so it's going to approach 0, but never cross it. And so basically the psi squared decreases with radius. And when you first learn this stuff, or at least when I first did, there's two strange things about this, I suppose. One is, I've said, the probability is never 0. You could have a hydrogen atom at the center of the room, and there's a non-zero probability of the electron being, on Pluto, right? So it's never going to go to 0, although of course it gets very, very small and very close to 0. But the stranger thing for me was that this probability density, it goes higher and higher as you get closer to the nucleus. So like, doesn't that just mean that the electron is going to crash in the nucleus? You told me in the Bohr model that doesn't happen. So this kind of goes against that. And the reason that this looks a little bit weird is because what you have to understand is that even though psi squared gets to larger and larger values as you get close to the nucleus, that also represents a smaller and smaller region of space. So even though it has a high individual probability of being close to the nucleus, there's not a very large volume right close to the nucleus. But as you get further and further away, the overall probability gets lower, but the region of space that it could be in gets bigger. So that's why when we talk about the radial probability density 4 pi r squared psi squared, you're multiplying together really two competing functions. Psi squared gets smaller and smaller and smaller as you go further away from the nucleus, but the r squared part gets bigger and bigger and bigger. So you're multiplying two different things together, one that gets smaller, one that gets bigger. So what you end up with mathematically is sort of a peak in the function. That looks like this. So the radial probability density actually approaches 0 as you get close to the nucleus, because that's such a tiny region of space that the electron would be in, and then it reaches some maximum value farther away. And so that value here is what we call the most probable radius. This is the radius from the nucleus, the distance from the nucleus that has the greatest chance of the electron being there. Now, it might not be a very high chance, but it's the one that would have the highest chance where that maximum is reached. So we call that the most probable radius. Again, the idea is not that the electron is always at that radius. It's actually not there very often, but it's the most probable. And it in the hydrogen atom equals 0.529 angstroms. Now, you don't need to remember that number, but what's interesting about that number is it's the exact same number that the Bohr model predicted as well. We didn't really talk about the distance aspect of the Bohr model too much, but that n equals 1 orbit in a hydrogen atom for the Bohr model was predicted to be exactly 0.529 angstroms. Angstroms is 10 to the minus 10 meters. So the number that you got from the Bohr model is the same that you get from this model. It's just thinking about things a different way. The Bohr model would have said in n equals 1, the electron is exactly 0.529 angstroms away all the time, moving in a circle, whereas in this sort of wave function model, that's the radius where it's most likely to be, but it can be found really anywhere at any given time. We don't know exactly where it is at any given time, but this is where it's most likely to be at that distance. Now, the other thing that we often define, as we said, is we don't really care about exactly where the electron is at any given time. We care about the region of space where it's most likely to be all the time. So what we often do is we take these probability distributions and we sort of consider like the 90%. So we shade in 90% of the area here, and we sort of define that as the orbital or the region of space where the electron is likely to be. So you consider where the electron is likely to be 90% of the time is typically how it's done. So that 90% probability region is sort of all of the areas around the nucleus where the electron is going to be 90% of the time based on this function here. And this 90% probability region has, of course, a distance associated with it. What distance from the nucleus is the electron likely to be 90% of the time within that distance, but also has a shape associated with it that we're going to start talking about. So for the hydrogen atom, it's pretty simple and not too different from the Bohr model, because this 90% probability region for a hydrogen atom ground state is just a sphere. So it's a sphere with some radius. So 90% of the time, the electron is going to be inside of that sphere, and it's a totally spherical shape. So we would say that the orbital that the hydrogen electron is in the ground state is a spherical orbital, and it's in this 90% of the time going to be within that shape. Okay. So again, these are mathematical functions, but we're going to start thinking about them more as shapes as we go along. And so for a hydrogen atom, it's a spherical shape. So to really then define all the different possible types of orbitals we have as we move on from hydrogen and as we move into multi-electron systems with many different energy levels, we want to think about them more as shapes to some extent. And the way that we do that is it's not going to be, again, very mathematically simple for us to actually consider these wave functions psi. I haven't even written out one of those functions yet, but they're very complicated, very difficult to deal with. Unless you're really, really good at math, it's going to be hard to visualize. This is my wave function psi. This is the shape of the 90% probability region. Those two things are hard to connect. So the way that we do that is these wave functions are parameterized in terms of what are called quantum numbers. So we already introduced quantum numbers for the Bohr model, n equals 1, n equals 2, n equals 3, n equals 4, which relates to, again, how far away the electron is from the nucleus and the energy level. And the same story, in multi-electron atoms, we also have quantum numbers that would help us define, on average, not exactly, but on average, how far away is the electron from the nucleus, what is its energy level, and as we'll see, what is the shape of that region where the electron would be 90% of the time. And those all come from what are called quantum numbers. The difference is for the Bohr model, we just needed one quantum number. For electrons and atoms, we need 4. And 3 of those that we're going to introduce first are going to define each individual orbital that we'd have, each possible energy level, each possible region of space where the electron could be. Okay? So what these quantum numbers refer to, they're a series of integers. The 3 that we need for defining an orbital are all integers. So it makes things a lot simpler because we don't have to remember complicated mathematical equations or interpret complicated equations. We just have to remember these integers. They all kind of have relationships to one another, but they're part of the wave equation psi. So psi has a bunch of different parameters in it, and these quantum numbers are those parameters that we can pull out that make it simple for us to understand. And just by knowing the quantum numbers, they all relate in some way, as we'll talk about. They allow us to describe the energy, shape, and orientation of an orbital. So basically, each of these quantum numbers tells us one or more of these things about the orbital and allows us to then start thinking about, again, where is the electron most likely to be? What is the relative energy if the electron is in that orbital versus a different orbital in the atom, okay? So the first one we're going to define is exactly the same as the Bohr model. The first quantum number was called the principal quantum number, is abbreviated as n, and it has the exact same allowed values, positive integers, 1, 2, 3, 4, and so on. So what we call this is the principal quantum number, or sometimes the first quantum number. And what it relates to physically is the energy and the size of an orbital. So again, if we're talking about the relative energies of orbitals, just like we saw in the Bohr model, n equals 1 orbitals tend to be lower in energy, n equals 2 higher, n equals 3, and so on. And it also refers to the size. How big is the region of space where the electron can occupy? It's going to be smallest for n equals 1. It's going to get bigger and bigger as your value of n gets larger and larger. A synonym for this that you might hear from time to time is the shell number. So if we say the electron is in the first shell, that means n equals 1 for that electron. Or if it's in the second shell, n equals 2. Now, an important distinction we have to make now that we're starting to talk about multi-electron systems or getting towards that is if you're in a hydrogen atom, or if you're anything that has one electron, but hydrogen atom being the most common one, obviously, that has one electron, the energy is exclusively determined by n, just like we saw for the Bohr model. So the equations we have for the Bohr models depend only on n, and that is still true. That hasn't changed for us. So if there's just one electron, n by itself relates to the energy level of that electron in the atom. Now, when we go to multi-electron systems, though, we need to use also a second quantum number to fully define the energy levels of the system. So for multi-electron atoms, you can't just use a single quantum number to tell you the relative energies. It requires both the principal quantum number n and the second one, which is abbreviated as L, usually a cursive L. So I'm going to write it like that. Okay, so it's lowercase l, but usually written in cursive for whatever reason. And when we start talking about these other quantum numbers, basically the values that they can have depend in large part on the quantum number above them. So depending on what your value of n is, you're going to have different values of L that are possible. So the values of L that are possible, they always start at 0, and they end at n minus 1. Or another way to think about this, if we don't like these greater than or equal to signs, is just it goes from 0 to n minus 1. So it depends on what your value of n is for that orbital is going to tell you how many possible values of L there are and what they are. So if n equals 1, your only value of L is 0, because 0 is the smallest value of L always, n minus 1 would be 0 as well, so there's just that single value. But if n equals 2, your L value could also be 0, but it could also be 1 because 2 minus 1 is 1. So depending on what your value of n is, that's going to dictate how many different L values you have and what they are, starting at 0 going up to n minus 1. So what does this L value refer to? From a quantum mechanical standpoint, which we don't need to worry about too much, is called the angular momentum quantum number. So it's related to the angular momentum of the electron in that orbital, but that's not a very useful way to think about it. What it really tells us, though, that's critically important for what we need to understand in this course, is this relates to the shape of the orbital. Now we're only going to do it for n equals 0, L equals 0, L equals 1, and L equals 2, because beyond that, the shapes get excessively complicated and don't really come up too often anyway. But each different L value has a sort of general shape associated with it. Spherical being the simplest that we already talked about, and then getting a little bit more complicated as we get to higher values of L. So that's really what L tells us is the shape. And it also contributes to the overall energy of that orbital whenever we have more than one electron. All right, and again, I want to emphasize that because it's a fairly important concept. When you have one electron, you only need the value of n to define the energy of that electron. That comes from the Bohr model. That's still true today. But if you have more than one electron, you need n and L together. Those kind of together allow you to define the energy of that electron, of that orbital. Okay? And then finally, the third quantum number that's used to specify an individual orbital is m sub L. And just like before, the values of m sub L that you can have, so it's m with a subscript L is how you sort of write it. They depend on the value of L. So this is the only one that can be negative. It starts at negative L and goes to positive L. And includes 0. All right, so you include 0 in that. So there's m sub L values that can be negative, positive, and you always include 0. So again, it depends on what value of L you have. That's going to tell you how many different m sub L values and what they are. This one is called the magnetic quantum number. Magnetic. So it only matters for the energy if you're in a strong magnetic field, which the magnetic field of the Earth is not enough to cause problems. So generally we can think about this one doesn't determine the energy at all, m sub L. But what it determines for us, which is important for certain types of orbitals anyway, is the orientation of the orbital. So for the orbitals that aren't spherical, which direction are they pointing is going to be determined by the m sub L value, okay? So that's what the quantum numbers sort of tell us and the relationships between each other. So let's talk a little bit more then about some of the terminology and some of the things that we get from this. So now that we have these three different quantum numbers, the ones that we often use together are going to be n and L. The second quantum number L, as we said, tells you what type of orbital you have. So if you have a pair n and L together, those are referred to, I'll write this right eventually, as a sublevel or subshell. All right, so if you just define n, that tells you what shell you're in. If you define n and L together, that tells you what sublevel or subshell you're in. Those are the terms we use for that. Now, the reason I'm introducing this right now is because typically we don't use the numerical value of L. We have letters that are used instead to abbreviate L. And I don't know why they do this. This is sort of, historical artifact that I have no control over, but this is the way that it's typically referred to. So each value of L, as we said, tells you what kind of orbital it is. The most common values of L that we have are 0, 1, 2, and 3. We can go up higher in some cases, but it's not going to be something that we see in our everyday life. But basically, the type of orbital or the type of subshell that we're in is going to be defined by L, and we use letters to describe them. So whenever L equals 0, we would say that that's an S orbital or an S subshell. Those kind of are used interchangeably. L equals 1 would be a p orbital or a p subshell. The relationship between subshell and orbital, in some cases, a subshell has more than one orbital in it. But if we say it's a p subshell, that's going to be a set of p orbitals. There's 3 of them in that case, as we'll learn. But L equals 2 is d orbitals or d subshells. L equals 3 is F. So those are the 3 that you have to remember pretty well. SPDF means L equals 0, 1, 2, and 3. And then when we go higher than that, it tends to go alphabetical afterwards. We don't see these in the ground states of real atoms anyway. So L equals 4 would be in G orbital, L equals 5 is H. It pretty much goes alphabetical after that. I think they skipped J, but we're not going to worry about that because you never go that high anyway. But these 4 here, 0, 2, 1, and 3, you have to remember them, and they occur in the types of atoms that we work with here on planet Earth. And those that are found in the periodic table over there all have these types of orbitals involved with their electrons being located in them in different combinations. So these 4 here are the ones you really need to worry about the most because they occur in the ground states of atoms. We keep making the periodic table bigger and bigger as more elements are discovered, but I don't think we've had to go up to G or H yet. Everything can fit within these 4 subshells here, S, P, D, and F so far. All right, so those are the ones that, but and most of the new elements anyway are man-made things that last for fractions of a second, so not very useful. So the ones that we care about are these 4 here. That's long story short. All right, so that's the when we talk about a subshell, it's subshell or sublevel, it's N and L together, and it's a specific type of orbital then that would fall within that. And so again, what I want to then finally get to here is this idea that there's relationships between the quantum numbers. Depending on what value of n you have, you're going to have certain values of L, and depending on what value of L you have, you're going to have certain values of m sub L that are allowed. So this is sort of another way of visualizing those rules that we talked about. All right. So let's just go through n equals 1, n equals 2, and n equals 3, and talk about all the different possible combinations of quantum numbers we can have within each of those. So if n equals 1, it's the simplest situation. So that's going to be the first shell. The L values that we can have go from 0 to n minus 1. So if n equals 1, as we said, the only value of L that we can have is 0. It has to start at 0. It goes to n minus 1. In this case, n minus 1 is also 0. So 0 is the only possible value when n equals 1. So that means when n equals 1, the only subshell you have is the 1s subshell. There's no other subshells with n equals 1 because L equals 0, which is s, is the only possible L value you have. And then for m sub L, this one goes from minus L to plus L. And again, if L equals 0, negative L is 0, positive L is 0. So there's only one value that we can have, which is 0. All right. So the first shell, n equals 1, only has one subshell, which is L equals 0, a 1s subshell. And then within that subshell, you only have one possible value of m sub L. So that means there's only a single orbital in that subshell. So that's the simplest one. But as we go higher, of course, there's more and more possibilities. So if we go to n equals 2, now for n equals 2, we have two possible L values. So that means there's two subshells with n equals 2. L can be 0, that's always the smallest value, but then it can go up as high as n minus 1. In this case, n is 2, so n minus 1 would be 1. So now there's two possible values of L, 0 and 1, which tells us that when n equals 2, we have both a 2s and a 2p subshell. L equals 0 for 2s, L equals 1 for 2p. Within the 2s subshell, we still have only a single m sub L value because the values of m sub L that we can have only depend on the value of L above it, not the value of n. And so if L equals 0 for a 2s subshell, m sub L can also only equal 0. So that 2s subshell still just has a single 2s orbital. But then when we go to L equals 1, which is our 2p, p is the letter that's associated with that L value, now we have three possible values because we can go from negative L to plus L. So negative 1 would be the smallest, plus 1 would be the biggest. We also still include 0 in the middle there. So we have three possible values of m sub L. Negative 1, 0, and plus 1. All right, and so what that tells us is that in a subshell that's defined with n equals 2, L equals 1, which we would call a 2p subshell, there are three different m sub L values, which tells us that there was three different p orbitals in that subshell. So as we go to higher values of L, the individual subshells can have more and more individual orbitals in them. So an s subshell only has a single s orbital, but now we see that p subshells would always have three orbitals in them because there's three different m sub L values. Each m sub L value specifies a unique orbital with a different orientation. And then finally, when n equals 3, we have now three different L values possible. We have L equals 0, L equals 1, L equals 2. So in the third shell, we have three subshells, 3s for L equals 0, 3p for L equals 1, 3d for L equals 2. And then when we go to the different possible m sub L values each of those have, once again, if L equals 0, m sub L only can equal 0. Just like the last one, when L equals 1, we have three m sub L values, negative 1, 0, and plus 1. So that means our 3p subshell also has three orbitals in it. The number of orbitals is only determined by the L value in that subshell. And then for L equals 2, we have five possible m sub L values, negative 2 to plus 2. So it's going to be negative 2 to plus 2 and everything in between. So there's five possible values. It's going to be minus 2, minus 1, 0, 1, and 2. So that means our 3D subshell, n equals 3, L equals 2, has five m sub L values, meaning that there's five 3D orbitals in that subshell. So that's what the number of m sub L values tell you. Each of these, as we'll see a little bit later on, represents a different orientation of that orbital. Okay, so any questions on that so far? So what you should be able to do, as you'll see on the homework assignment, not probably till next week, is if we give you different sets of quantum numbers, you can make predictions about other possible quantum numbers that would be able to be along with those and what sort of just think about what that means as we'll see more and more of. So let's just do a couple of example problems, one or two examples. So how many subshells have the principal quantum number n equals 3? So this one is, if you know, these are some of the relationships we have to start thinking about now. How many subshells have principal quantum number n equals 3? Well, we just saw it on the previous slide, but a subshell, remember, is defined as n and L together. So for n equals 3, we have to figure out how many different L values there are, and that's going to tell us how many subshells there are. So for n equals 3, we just saw that L starts at 0 and goes to n minus 1. So these are the 3 possible values of L. So that means there would be 3 subshells with n equals 3, okay? And as a general relationship then, the number of subshells in a given shell is just equal to n. So when n equals 1, there's only 1 subshell. When n equals 2, there's 2 subshells. N equals 3 has 3 subshells. N equals 13 has 13 subshells, right? It works all the way up. And that's because there's that many different values of L that you can have depending on what your value of n is, okay? So the number of subshells in a shell is just equal to whatever that value of n is. That's as simple as that. So learning some of these relationships that we're going to cover in some of these problems can be helpful. You don't have to memorize them all as long as you know the rules for quantum numbers, but they can help you save time and make sure that you're on the right tracks in cases. So now if we go to a slightly more complicated example, how many orbitals are in the third shell? So we said there's 3 subshells in the third shell, but how many total orbitals would there be within that? So we have to remember that here an orbital is defined by an entire set of 3 quantum numbers, n, L, and m sub L. So each individual orbital is going to have a unique set of NL and m sub L values. So what we could do for this problem is we could write out for n equals 3 all the allowed combinations of NL and m sub L. That would take a little while and be open to mistakes. We actually already did that. So if we go back to that tree that I drew earlier, we kind of already did that. So if n equals 3, we can have L equals 0, 1, and 2. M sub L can be these possible values. So if we count on here, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 unique possibilities within that. But again, it might take a little time to write all that out. Even if you go n equals 3, that's already 9 things you have to worry about getting right, not missing any. So I think that's where it's helpful to learn some different relationships that are useful as well. So if we're given an n value, so if we're telling you what n is, or telling you that you're in the second, third, fourth, whatever shell, which defines your n value, we can say that there's a general relationship that the number of orbitals in that shell equals n squared. Okay? So for this one here, third shell, n equals 3, so 3 squared equals 9. So there would be 9 orbitals with n equals 3. If you go back to that tree, there would be 3s, 3 3p orbitals, 5 3d orbitals for a total of 9. Okay? Now, another relationship that could be helpful, doesn't come up in this problem, but I'm going to put it here just for completeness, is that for a given L value, number of orbitals is given as 2L plus 1. All right, so if we're defining a sublevel, which has an N and an L value, or just giving you an L value by itself and saying how many orbitals are there with that L value, then it would be 2L plus 1 is the relationship for that. So as an example of that, within this third shell, if we consider the 3D subshell, for the 3D subshell, L equals 2, which means that the number of orbitals is 2 times 2 plus 1, which is 5. And again, that's because there would be, this question didn't exactly ask that, but I'm just giving this as an example. That's because there's 5 possible m sub L values. So whenever L equals 2, whether it's 3D, 4D, 5D, whatever D subshell it is, when L equals 2, there would be 5 orbitals in that subshell. So as we said, for the 9 orbitals that you have with n equals 3, one of them is a 3s orbital, 3 of them are 3p, L equals 1, so there's 3 of those. 5 of those would be 3d, so 1 plus 3 plus 5 is your total of 9 orbitals. So that's kind of these relationships that we're going to start understanding. All right, so then last example question for now, right? No, keep going. How many f orbitals are in a given f sublevel? Well, again, if we're giving you a sublevel or just an L value, anytime you're given the value of L, whether or not it's attached to an N value or not, if you have the value of L either given directly or indirectly, we're going to use the 2L plus 1 relationship. So F, remember, is L equals 3, because L equals 0 is S, P is 1, D is 2, F is L equals 3. So then we just use the 2L plus 1 relationship to figure out how many F orbitals would there be in that sublevel. 2 times 3 plus 1 is 7, because L equals 3 there. So that would be letter D here. And again, it doesn't matter what type of F sublevel is it. 4F is the first one. It doesn't matter if it's 4F, 5F, 6F. If you know that it's an F sublevel, there will have to be 7 orbitals in that sublevel. Yeah. Well, if we're asking you how many orbitals are in a sublevel, we have to define which sublevel we're talking about, which means you have to have the value of L. Now, I didn't give it to you here as a number, but remember that each of these letters corresponds to one of the sublevels. So whenever you have an F sublevel, whatever the value of N is, that means L equals 3. So in order to use this relationship, you have to know which value of L we're talking about. Because if you're in, if you're in the fourth shell, for example, you're going to have 4s, 4p, 4d, and 4f subshells. And if I want to ask you how many orbitals are in one of those subshells, I have to specify which one I'm talking about, right? So if you're talking about orbitals in a subshell, the value of L has to be specified either as a number or here it's given in the letter form, which is more common. Okay. Yep. The number of sublevels is determined by the value of N that you have. So the number of sublevels in a shell is just the value of N. So N equals 1 has one sublevel, N equals 2 has two sublevels. Here we didn't specify the value of N, but we didn't have to, because if you're talking about the number of orbitals in a sublevel, it only depends on the L value. It doesn't matter what your N value is. But for any F subshell or sublevel, there will be 7 orbitals. And that's just given by this relationship here because it only depends on the value of L that you have. All right, anything else? All right, now for real, the last example problem for now. How many orbitals have quantum numbers N sub L, N and L together equals 7 and 5? And again, this is a situation where all we really care about is the value of L here. Because if we're giving you an NL pair, here it's given to you directly, the number of orbitals in a sublevel, which is defined by N and L, is just given by that 2L plus 1. And again, that's because N and L define a sublevel, and for the number of orbitals in a sublevel, it only depends on L. So this is the exact same type of question, just asked in a little bit different way. So here what we have is 2 times 5 plus 1, because L equals 5 in this pair, is 11. So there'd be 11 orbitals in the sublevel. Again, the value of N doesn't factor into that at all. Anytime L equals 5, then there's going to be 11 orbitals in that sublevel. All right, so that's just a slightly different way of asking the same thing. So what we're going to move on to for the rest of today are the shapes of the atomic orbitals. And again, well, this is sort of what we're sort of thinking about here with the shape of an orbital is the region in space where the electron is likely to be like 90% of the time. It's not always defined that specifically, but that's sort of what we're thinking about. Where in space is that electron most likely to be? And again, there's going to be different shapes that are going to be determined by the value of L. So first, a few terms that we need to know to understand this. A node is a region where the electron has 0 probability of existing. Now, this is one of those sort of far out things about the quantum mechanical model of the atom, which is that there's going to be some places where the electron has 0 probability of being, but it has a non-zero probability of being on either side of that. So how does it hop through without, going through that region of 0 probability? That's called tunneling. It's kind of a far out thing, but basically that's what we mean by a node. It's a region where the electron has 0 probability of existing. And there's two types of nodes we have to understand. So the first one is a radial node. This is going to be a certain distance or radius from the nucleus, r. Again, the nucleus is our origin point, and a radial node is a certain distance from that where the probability of finding an electron is 0. And as we'll see in some of the examples that we draw out, the number of radial nodes is n minus L minus 1. It's the number of radial nodes is not critically important, I would say, for most things we do in chemistry. Where are the radial nodes? We don't really care. It's going to relate a little bit to what we talk about later on with the relative energies of these different orbitals, which we'll talk about next time. So it kind of comes into play there. It's not something that we have to think about a lot, though, but that's what is given by n minus L minus 1. So the number of radial nodes for an orbital depends on the n and L value together. Okay? And then a nodal plane is a two-dimensional plane where the electron has 0 probability of existing. And it's these nodal planes that give the orbitals their different shapes. So if you have 0 nodal planes, then it has to be a sphere. But as you start introducing nodal planes into the picture, then you start getting shapes that are not spherical for some of the orbitals, as we'll see. And as we already said, the value of L determines the shape of the orbital. So then, not surprisingly, the value of L determines how many nodal planes you have as well. So the number of nodal planes is just equal to L. That's a simple relationship. So if L equals 0, there's 0 nodal planes. That means that region of space has to be a sphere. There's no two-dimensional region where it can't be. But if L equals 1 or 2, as those are the other ones we're going to talk about today, then you have 1 or 2 nodal planes, and that's going to then change the shape of the orbital from something spherical into something a little bit more complicated. So let's talk about radial nodes first, and we're going to do that with the s orbitals. The s orbitals are the simplest ones. L equals 0. And that means that they're spherical in shape because there's no nodal planes. So any s orbital, whether it's 1s, 2s, 3s, 4s, and so on, is going to have a spherical shape for that orbital. But the difference between the different s orbitals, 1s, 2s, and 3s, and so on, is how many nodal planes, how many radial nodes they have. And that's going to then give them different probability distribution functions, 4 pi r squared, L squared. So if we have a 1s orbital, the number of radial nodes is n minus L minus 1. So L is always 0 for these, so 1 minus 0 minus 1 is 0. So a 1s orbital has 0 radial nodes, and its probability distribution function is going to look a lot like what we saw for the hydrogen atom earlier. It's just going to have a peak at some radius, the most probable radius where it's most likely to be, and it just looks like that, like we drew earlier. But if we get to higher order s orbitals like 2s, here we have n equals 2 and L equals 0. So 2 minus 0 minus 1 is now 1 radial node. I guess it's not just, I guess Teams does this too. Crap. All right, let me. Seems like yeah, the pen's not working anymore. All right, I'm gonna have to reset this. That's a little bit too early for us to end today. So maybe I shouldn't have stopped that since I did it in 2 parts, but I'll combine them if they're not combined by Teams automatically. And then I just have to share screen so people in Teams can see what I'm doing. All right, I think we're about ready. Let's get this in full screen. All right, picking back up. That was roughly a 3-minute delay, so not too bad. If we go back to now the 2s orbitals, we have, as we said, 1 radial node. And so what that means is they're still spherical in shape. The overall shape doesn't change. Any s orbital is going to be spherical. But now there's going to be a certain distance from the nucleus where the electron has zero probability of existing. So you can almost think about in 3 dimensions, it's like there's sort of two concentric spheres where there's like a little radius where the electron can't be. But what that means in terms of this two-dimensional function is that it's going to have some peak close to the nucleus. It's going to go to zero and then have a larger peak further away. So this there where it goes to zero, that's your radial node. Again, it's a probability where it's a place where that probability, that 4 pi r squared psi squared goes to zero. And that's what 2s would look like. And then 3s, just continuing the pattern, n equals 3, L equals 0, means that we have 2 radial nodes. So it would look like this. You'd have 2 little peaks that go to 0 where the radial nodes are, and then a bigger peak further away. So one thing I didn't convey very accurately here, but is true, is that as the value of n gets larger, 1s, 2s, 3s, the shape stays the same, but the number of radial nodes increases, and that most probable radius does get further and further away. So I didn't do a careful job of showing that. But for 1s, this peak here is going to be closest to the nucleus. Then it's going to get a little bit further away for 2s, even further away for 3s. That's what the value of n also sort of relates to. But those are the s orbitals, which are, again, are the simplest ones. You have to think a little bit about radial nodes at times, but the shape is just spherical, so that's not too bad. Now, if we go to the p orbitals, we'll talk specifically about 2p orbitals, but any p orbital would have this same basic shape. So for the 2p orbitals, L equals 1 for p, and that means we have 3 possible m sub L values, -1, 0, and +1. So that means there's 3 individual orbitals, and each of them is going to have 1 nodal plane. In terms of radial probability density for a p orbital, a 2p orbital specifically, L equals 2, L equals 1, we still have 0 radial nodes. So if we wanted to draw the radial probability function, it would look very similar to 2s. It would be, probably a little bit further away because it's n equals 2, but still just a single peak, no radial nodes. But we don't care so much about the radial probability especially for orbitals that aren't s orbitals. What we want to care about is the shape. So when we have one nodal plane, what that means for us is that the radial probability function is not constant in all directions. And there's a nodal plane where it's a two-dimensional plane where the electron can exist. And what it really results then is that these p orbitals have sort of a figure eight, or what's sometimes called a dumbbell shape to them. So they look kind of like this. So the way that they're sort of oriented is differently. And so you're going to have one orbital that looks like this, where you have now 2 different lobes, ideally the same size. I didn't do a perfect job. And I'm going to shade them in different colors. Your book doesn't always do that, but I think it's important to note that what this refers to then is when you have a nodal plane that goes through the YZ plane, it cuts it in half like this, the sign of the wave function changes as you go through that nodal plane. So in one direction is positive, one direction is negative. That doesn't matter so much for what we're doing now, but when we start talking about how orbitals combine to make bonds, that's useful to think about. So I'm going to introduce it here. But basically, the probability density is the same on each side because it's just determined by psi squared, but the sign of the actual wave function does change. But we have one here that's oriented along the x-axis, so we would call that the px orbital. And the nodal plane then would be the plane that's perpendicular to that, which is yz, the other 2 coordinates. And so then the other 2 p orbitals that we have, there's a total of 3 of them because there's 3 m sub L values. They look exactly the same as this. They're just pointing in different directions. So we would have one that goes in the y direction, which is py. So the same exact shape, but now just pointing in a different direction. It's 3-dimensional, so you have to think about it in those terms. It's kind of like putting 2 balloons together and sort of joining them where the tie is for the balloon. So it's kind of like 2 sort of oval-shaped things protruding in 2 different directions. And this one goes in the y direction, so we call it py. And the nodal plane would be the other 2 coordinates, x and z. And then finally, we have one that goes vertically in the z direction, as I've defined the coordinates here. And again, we're shading one of the lobes, which just indicates that the sign of the wave function is different in the positive and negative directions. Not so critical right now, but will be more important in the future. And so we have, this is called, sorry, PZ. We're in the Z direction now, which has an XY nodal plane. So whenever you're in a P subshell, you have three individual orbitals because there's three different M sub L values, and they're all shaped the same because they have the same L value. L determines the shape, but they're oriented differently in space. And that's how it's going to look for any of the P subshells. Three identical orbitals, but oriented differently in space. Now, one thing to keep in mind is there's not really a direct one-to-one relationship between which M sub L value corresponds to which of these P orbitals. It's not that this is M sub L equals minus 1, 0, plus 1. There's no real clear relationship there, which is partly because of we're parameterizing things X, Y, and Z, but the M sub L values come out of the polar coordinates, so it's more complicated. But anyway, don't worry about that. Just know that there's three P orbitals, one in the X direction, one in the Y direction, and one in the Z direction. And then the last ones that we'll cover, and this will be the end of today, are the shapes of the d orbitals. And again, if we're starting with 3d here, n equals 3, L equals 2 now for d orbitals, we'll still have 0 radial nodes. But now you're going to have L equals 2, so that means you have 2 nodal planes. The number of nodal planes is equal to the value of L. So that's going to make the shape more complicated. You're still going to have a very similar radial probability density, but again, it's not the same in all directions because you have these nodal planes here. So for the d orbitals, you have two nodal planes, and what that then means is that for 4 of the 5 d orbitals, you have a 4-leaf clover shape. You basically have 2 planes that cut it in half in 2 different directions. That gives you sort of a 4-leaf clover type arrangement. And the way that they're named is a little bit, it's fairly intuitive. So we'll start with this one here, which is dxy. So as the name suggests, this orbital is going to primarily be oriented in the xy plane. It is three-dimensional, so it has some magnitude in the z direction as well. It's not totally flat, but it's going to be sort of in the xy plane primarily, and it's going to have its lobes going in between the x and y axes. So this is x, this is y, so the xy orbital is going to go sort of in between those axes. I have to try to draw it in 3 dimensions, which is not always easy. It's going to look something like that. It's a 4-leaf clover, and then alternating positive and negative signs. So we're going to shade every other one like that. So that's dxy. And that's going to, again, involve these 2 coordinates here, x and y. If we go to the other d orbitals, those ones are going to be 3 of the 4 remaining ones are going to be shaped the same, just oriented differently. So we have one that's in the YZ plane. So we'll highlight those 2 axes, and this one's going to be called dyz. And its lobes are going to be in those directions, in between the axes still. And again, these are, you have to think in 3 dimensions for this, so it's not the simplest to visualize, and it's also admittedly not the simplest thing to draw. But basically, it's another 4-leaf clover shape, but it's just oriented in a different direction. XY would kind of be flat as I've drawn it in the plane like this. This one's sort of pointing up. And then we have a YZ, which goes in the, sorry, XZ, I'm getting these confused again. X and Z goes through those axes there, and would have lobes in between the X and Z axes. So they're just, again, oriented differently in space. I don't think I did a great job with that one, but yeah, that's close enough. All right. And then those 3 are just, again, they're all shaped the same, and they're just in different Cartesian planes. We have one other one that's in the xy plane. It's called dx squared minus y squared. It's just this orbital here rotated 45 degrees. So instead of having its lobes between the axes, and this one, the lobes are right on the axis. So you have one in the x direction, one in the y direction, in both positive and negative. So the lobes are right on the axis, and again, every other one is shaded. So 4 of the 5d orbitals look exactly the same. They just have different orientations of space. The name kind of tells you a bit about how they're oriented. For these 3 here, the name of the orbital is the name of the plane that it's primarily sitting in. X squared minus y squared is not as intuitive, but it's in the xy plane, and it just has its orbitals lobes directly along the x and y axes instead of in between like this one here. Now, the last d orbital is a little bit of a weird one. It doesn't have 2 nodal planes. It actually has 2 nodal cones. So its nodal planes are cone shaped instead of being just flat planes. And so this one is called DZ squared. And what it looks like is it kind of looks like a p orbital at first. It just has this sort of four-leaf clover shape. Not sorry, this sort of dumbbell shape. I don't want Acrobat open now. Thank you. But in this case, the opposite lobes are the same sign, so you're not going to shade one of them. And what it also has is what's called a torus, or colloquially a donut, that goes around the middle of it. So it's kind of like a figure eight wearing a hula hoop, or like a life preserver kind of thing around the middle. And that's what this little ring is that I've drawn here in blue. So that has the opposite phase. So DZ squared looks like that. It looks different than the rest of the d orbitals, but what it actually has instead of nodal plane is nodal cones that kind of go out like that and like that define the shape. So in case those drawings don't work for you, your book has them, and I've reproduced them here from, I don't know if this is your book or a previous version. Again, your book doesn't always do the shading, but this can hopefully help you understand them a little bit better. All right, so that takes us to the end today. We'll pick up next time with talking about how to put electrons into these orbitals.